So when you were discussing functions back in earlier grades, right, the first thing that you must have probably done is to know the types of functions that we have, right? Now the types of functions that we have, first of all, remember you got a linear or a straight line function. Linear or a straight line function. But I say to you, how do you know something is linear or straight line? Is if you are given an equation like that, the highest degree should be 1. If the highest degree, if the degree is 1, then it means that thing is a linear function, not the highest degree. If I say the highest degree, that is wrong English, because degree on its own, right? Degree means the highest exponent, right?
Okay.
Yeah, so if the highest exponent is 1, then that tells you that you are dealing with a linear function. The number 2, it could be a parabola or parabolic function, or which is also called a quadratic. And then how do you tell that it is like that? That is if the highest degree, oh my goodness, the degree is 2. Yeah. The degree is 2. Why am I saying the highest? Okay, number 3, you're gonna deal with a cubic function, most definitely, now that you're in grade 12, and that is the degree will be 3, right? Polynomial function is a degree equal to 4, but that one will be left for varsity. And then now number 4, we have exponential functions. Now that is when the x is an exponent itself. You see, if the x is an exponent itself, then it means it's an exponential function. It doesn't matter what the base is. I just chose 2, but it could be any base. That is why sometimes we prefer just to write b there. Man, to be honest, I don't know, I enjoy this board more than the other one, Right. Number 5, hyperbola, So hyperbola also, this is where you find your what, that there the x is a denominator. I'm just gonna choose, let me just say a. So if x is a denominator, then you know that you're dealing with a hyperbola. So these are the types of functions that we have. Now, as much as we have those functions, I now look at this, man. In this nice, man. So as we have those functions, right, you then have to know how to sketch them. Now, sketching functions is not something that is a bit of a headache that much, because there, what you should just remember or know, number 1, you need to find, there are 2 methods, by the way. You can decide to use the table method, which works 100% of the time. So the table method. Now the table method is quite easy, because there you simply have to have your table there like this, and then you draw a table like that, right? And then you find yourself just having x and y values, right? So you let x and then y values, and then I usually start from -3, then you go all the way to 3. Then you'll be finding your values. So like -3, -2, -1, 0, 1, 2, 3. You find the corresponding y values. Those are your coordinates, and then you sketch the graph. That is a table method. Quite simple. And then number 2, you can use the calculation method. So calculation now, that means you do such as things as finding the y-intercept. You find the y-intercept by doing what? By letting x be 0. Then number 2, you can find the x-intercept by doing what? By letting y be 0. And then you can find you can either find the turning point. Now it will depend on the type of graph, but you can find the turning point, right? Or you can find the asymptotes, right? You can find the asymptotes. These 4 things are going to assist you to sketch a nice graph if you're using calculation, and then the table method also quite works. Right, now that is great. So now there is this question that we like to ask in maths. We do like to ask to say, okay, we are doing functions, but what exactly is a function? How is a function different to a relation? So function versus relation. Do you perhaps have any idea them?
No.
Say what is a function and then what is a relation. Well, a function is just a relationship between the input and the output, okay? However, that relationship must be a bit defined to say how many inputs, how many outputs. I teach this grade 5 learner of mine, and they are starting to do in grade 5. The topic is called, you did this in grade 5 by the way, the topic is called flow diagrams. It's called flow diagrams. You did them in grade 5. So what you used to do, just to refresh your memory, there used to be boxes there. I'm just gonna make 3 boxes, and then these boxes, they are connected, and then they say there is something here which they called a rule, right? They called it a rule, and then it yields, it's a flow diagram because we start here, then we go there like this. Then it yields the following. So we get another one here, then we get another one there, right? So let's just say here we had a 6, 8, and then we had a 10, and then our rule says add 2, right? You can even say multiply something, but add 2. So what the answer that you would get there, I believe you can say 8, and then you can say 10 there, and then you can say 12. So these were used to be called now the inputs. This side, these were the inputs, and then these outside there would be the what? The outputs. So this flow diagram tells you that what you input into the rule yields the result as the output. What you input into the rule yields the result as the output. The very same idea was extended to functions to say the input was given a name now, to say the input will be x while the output will be y, while the rule is gonna be written like this. I want you to see something. If the input is x, the output is y. Do you agree? Do you agree that y is actually equal to x plus 2?
Yes.
Isn't it? Because x is the input, and then your rule is here. You add 2, and then you're gonna get the output as y, isn't it?
Yeah.
Great. So that is why this thing that you see here now, this is what we then call a what? A function. However, these flow diagrams that you see, they can be in 2 ways, right? I'm gonna quickly show you how different they can be, and to make that a bit faster, right? I can say, let me say you have this, you have that, and then you have that. And then let's say you have a rule here, and then you have an output, maybe an output and output. Let me say here you got 10, you got 5, and then let's say you got 6. Now let's say you're multiplying. Let me have numbers that are nicer. Let me just erase real quick. Let's use let's use 10. 5 is 10, and then let's use 20, and then let's use okay, yeah. So let's just say here you're multiplying by 2, right? So 5 times 2, oh, it must be this side. 5 times 2 is 10. And then this is not what I wanted, man. Okay. Okay, let's fix it like this. I got it now. It can't escape. Wait. 6. The ones I want are not. Okay, you know what? Let's do it this way. What I'm trying to explain there is that there are certain flow diagrams whereby one of the input yields the same output, like this input here, ne? If it goes through the rule, both of them, they produce the same output. So 2 inputs producing the same output, right? That is the first thing you can have, output. You can also have a situation whereby 2 outputs result from 1 input. You see, there are those type of situations, and that's where we find the difference between a function and a relation. And then to make it much simple and easy now, you must know that if you have 2 x values mapped to 1 y value, then this is a function. If you have 1 x value mapped to 1 y value, then this is a function. However, if you happen to have let's say 1 x value mapped to 2 y values, then here it's not a function, it's a relation.
How is it possible that 2 y values can result from 1 x value?
That's a very good question there, and we're gonna see it in a second. But 2 x values mapped to 1 y value makes sense, né? Because let's say I can have a parabola like this. If I have a parabola like this, and then I have a certain y value here, this y value can be mapped to this x, and you might find that maybe this x is 2. And the same y value can be mapped to this x, and you find that this x here is -2. Do you agree with this?
Yes.
So that would be 2 x values on 1 y value, and then therefore it's a function, right? It's a function. Then for the second part now, you can have something like this. 1 x. This one is a simple and straightforward. That you have, maybe we're just talking about a straight line, whereby on a straight line 1 x value is mapped to 1 y value, 1 x value is mapped to 1 y value, like that. So that would be a what you call a function also. But then now we have what you call a relation. A relation now is when you have 2 y values mapped to 1 x value. Now as an example, I want you to look at this. A circle. I want you to look at a circle. Or maybe one of my favorite functions of all time. And when I show people this, they're like, it does not exist. Yeah, it's because they've not reached varsity. You reach there and then you find that there is actually a function that looks like this. Aha. You see this one? I like it a lot. I like it a lot. So both of these are not functions. We call them relations. Why? Because I want you to check if there is an x value here, it's going to be mapped, right? It's going to be mapped to this y value. At the same time, it's going to be mapped to this y value. What we mean is that if you had a point here, the x of that point is going to be mapped to this y here. So I'm going to call it x1, y1. Then if I have another point here, the x here is going to be the same as the x that is there. Do you agree? Because it's a vertical line.
Yes.
And then this is y1. But then now here there is y2. So now it's mapped to y2 there. Are you able to see that?
Yes, I can.
Then now x1 and then it's y2. So now one x value is associated with two y values. So that means that thing is a relation. Same thing with the circle that you see here. It's gonna have a point here and a point there. Those points are gonna have the same x value, but they're gonna have different y values. So that means they are not called functions, but rather they are called relations. And Mina, for me to remember it quite easily, I always say that I take x as a lady, yeah, take x as a lady, and then I take y as a man. Now, as a man, right, you can either have one wife, right?
Yeah.
Or you can have how many wives?
Many.
Or you can have two wives as a man, isn't it? Like this.
Yeah.
So this is very much accepted in maths. I'm not saying, Mina, I know we are religious, so I'm not saying some, it just as a disclaimer, one the views expressed here are purely maths based. So so one lady and one man, good. Two ladies and one man, very much good. That means two ladies and one man, we're talking about a parabola, right? And then here we're talking about a straight line. However, you cannot, right? You can't have two men. Let me write a man here. You can have two men, right, with one lady. You see now it's two men and one lady.
Yes.
This now is not allowed. So this is called a relation. So two y values and one x value is not allowed. That is called a relation. That is called a relation. Right? So that is what we have there. That is the difference between a function and a relation. So it's a function here. Then it's also a function there, and then these two, then there you got a relation, and then that is what we have. So I'm gonna write this as x, and then y, and then xx, and then y, and then 1x, and then 2y values, which is not allowed. So how do you tell whether something is a function or something is a relation? There is actually a way of telling whether something is a function or something is a relation. So we're going to use two tests, right? The test that we use, number one, is called a horizontal. Sorry. We start with a vertical line test. So we have a vertical line test. And then vertical line test, what it's going to tell you is that whether something is a function or not, or a relation. Now, if it happens that something is a function, right? If something is a function, then we have to perform a test, which we're going to call a horizontal line test, right? A horizontal line test. Now a horizontal line test now is going to tell us whether that particular function is, number one, that particular function Is it a one-to-one function, or is that function a many-to-one function? Is that function a many-to-one function? So that is what you do. So as an example, I'm gonna give you, we're gonna do some bit of examples. Let me see if I can actually take some. So here we go as an example, right? So we are given there different functions, and now we have to test whether these things are functions or not. And if it's a function, we have to tell whether it's a one-to-many, it's a one-to-one or many-to-one, right? So you have to remember what we've already discussed so far. We said the first thing that we do when we're testing, right, you test whether something is a function or a relation. So how do you know, right? Use a vertical line test. I should really have a ruler here. Here's my ruler there. So this ruler, I'm just gonna turn it vertically, because remember it's a vertical line test. So I make it vertical. Not that perfect, but yeah. Here's a ruler here. Now we're gonna start on A. So if this ruler touches the graph only once, then it's going to be a function. If the ruler touches the graph twice, right, then it's gonna be a relation. So let's see, that is what we call a vertical line test. We are starting with a vertical line test. So let's see, is it gonna allow? I want you to check something. As the ruler is moving to the right, wow, look at how it's moving. Is it cutting the graph twice or once? Is it touching the graph twice or once? I mean, check. It's touching the graph. It's once. Now I want you to check. It's only touching once. Then I'm gonna move it. It's only touching once. Then I'm gonna move it. At each point, it's only touching once. Then I move it again. Wow, man. Very nice. So it's only touching once. Then therefore we can agree that actually this thing, it is a function. Then we're gonna come back and tell whether that function is a one-to-one or many-to-one. Let's move to the next part. Let's move to this one. Now I'm gonna move it to the right. It's touching how many times?
Twice.
So it's touching twice. So it's touching here, and then it's also cutting there. So because of that, and it's doing that throughout. So because of that, you see it's touching there, it's also touching there. So that means this thing that we are looking at, is it a function?
No.
It's not a function. So what is it? So what is it?
It's a relation.
So it is a relation. It's not a function. Right? So relation, that will mean not a function. Perfect. Then we move to the next one. Let's look at this one here. If I'm moving to the right, it's touching how many times?
It's one.
Only one. Only one. Perfect, perfect. Indeed, it is only one. It touches there. I move it to the left. It only touches there. So it's touching once. So we can agree that this is a function, right? It's a function. Then let's go further. Now, let me take my ruler. Let's go to this one. It's touching how many times?
So twice.
It's touching twice. So it means it's there and it's touching there. So this means that thing there is not a what? It's not a function. So we can call it a relation. That is a relation. I hope it's clear. So now that we know what is a function and then what is not a function, so to tell whether something is a function or a relation, we use what? Use the vertical line test. The vertical line test. Now, how do we tell whether something now which is a function, whether it's a many-to-one or a one-to-one? So there, remember, we use what you call a what? To tell whether that function is a one-to-one or many-to-one, meaning that if it's one man and one lady, or if it's one man and two ladies, ne? So that we use a horizontal line test. So that means our ruler now, we must flip it. So here we are. I'm gonna turn it to be a horizontal ruler. I mean to face horizontally. Yeah, virtual rulers. So this ruler now, for me to tell whether this function is a 1-to-1 or many-to-1, I'm gonna move it up now. That is the horizontal line test. If I'm moving it up and it's touching the graph twice, then that means it's a many-to-1. So what is this one say?
It's a many-to-1.
It is a many-to-1. It is touching twice. Sometimes it's even touching 3 times. So it means this thing here, it's a, let me use perhaps red again. So this is a many-to-1 function. And then this guy here, if I'm moving it down, how many times is it touching?
It's touching once.
So what type of function is that?
It's a 1-to-1.
Perfect, perfect. So that will tell you that this is a 1-to-1 function. Congratulations, man. Now you know what is a function and then what is a relation. And then now you know how is something a many-to-1 or a 1-to-1. That information, why is it important? Well, it is important because we're going to talk about inverse functions of a parabola. And you will see that why, let me not jinx it. Jinx what? You will see it. They will tell you, you will see it. When they talk about restriction of the domain, you will totally understand why. Okay, but for now, let's just look at a bit of functions that are, let's look at a bit of inverse functions. Like we already know that a straight line is going to be y equals to mx plus c as a straight line. Or you can even write it as y minus y1 m into x minus x1. Well, this is mostly in analytical, right? But for now in functions, we prefer this one, of which you can write as maybe f of x equals to ax plus q. That is the general formula for a straight line. So how I personally prefer to have inverse functions, it's quite in a bit of a simple way. So we're gonna have our first example. Let's say number 1, we're dealing with y is equals to 2x plus 2. Right, let's just call it f of x again. So let's call it f of x is equal to that as our first function. Now we need to find the inverse function. First of all, there are 2 ways of finding the inverse function. So if you want the inverse function here, number 1, you can use the table method, or you can use the calculation method. Which one do you prefer?
Calculation.
Calculation. Yeah. That's a wise choice. So let's see. We have y f of x is equals to 2x plus 2. The first thing, if you're going to engage in calculations, I want you not to write this question like this, but I would like you to actually write it normally as y is equals to 2x plus 2. You will understand why in a bit. So when you're using calculation or the calculation method, the first thing you're going to need to do is to say, let's find the equation of the inverse. Remember, this is the original. Just gonna write here that this is the original function. So you're gonna try and find the equation of the inverse. And then how do you get the equation of the inverse? It's quite simple. I always write this in my book. I write inverse and then I write dots. After writing those dots, then I say swap x and y, because the inverse function is just swapping x and y. So how do we swap x and y? Remember, the original is y is equals to 2x plus 2. When I swap x and y, I'm going to write it as x is equals to 2y plus 2. Do you agree?
Yes.
Where I see y, I put x. Where I see x, I put y. After swapping x and y, Number 2, make y the subject. Okay, make y the subject. And then to make y the subject, that means you're gonna have x minus 2 is equal to 2y. I took the 2 to the other side to change the sign. Then I divide by 2, I divide by 2. Therefore, my y is equal to x minus 2 over 2. This now is the equation of the inverse. That is the equation of the inverse there. So because it is the equation of the inverse, for it not to look like this, because if I say y is equals to 2x plus 2 and then y is equals to that, it's like I'm talking about the same y. To differentiate them, that's when we say, therefore, the inverse of f is equal to x minus 2 over 2. So we replace the y with the symbol f inverse. Is this clear, sir?
Yes. So do we not just say f to the power of -1, or would that be wrong?
F inverse of x.
F inverse.
Yeah, saying f to the power -1. Hey, I feel like you can say that, but it's a long way of calling it. yeah. So I can just say f inverse of. These symbols are very weird, but that is how we find the inverse there. That was the first, and I like to do this with two things so that at least we repeat the process and get familiar with the process. That was the first original. So I'm just gonna quickly take maybe another one. Let's just say you have half x minus 3. Make it a bit interesting as our original here. So I'm gonna say this is the original. Now for us to find the inverse, remember, this is k of x, by the way, k of x. So to find the inverse, I like to write inverse, and then I say I'm gonna swap x and y. Obviously right now I'm saying it, but when you are now used to it, you just swap directly. So you swap x and y, you're gonna say x is equals to half y minus 3. After swapping, you then say make y the subject. Make y the subject. And to make y the subject, that means I'll take the 3 to the other side, so I'll have x plus 3 equals to half y. And then now what I'll do, which is very, very slick and smart, is to multiply by 2 both sides. Okay, so if I do that, I'll end up having the 2 cancelling the 2, then I'm left with y, right? And then here 2 times x is 2x, and then 2 times 3 is going to be 6. So therefore my inverse now would be what? Would be k inverse of x equals to 2x plus 6. So this is the inverse, while that one is the original. I hope the procedure is clear.
Yeah, no, it's very clear.
Perfect. Swap x and y, make y the subject. Swap x and y, make y the subject. So now that we have the equation, now we have to sketch it. And now for us to sketch it, it's going to be quite simple. You only need 2 things. Let me just not hide it. Let me put it there. So now we need to sketch it. It's gonna be simple. Since you chose calculation, we are going to continue with calculation to sketch it. The only 2 things you're gonna need is the y-intercept. And then how do you get the y-intercept? We start by saying let x equal to 0. That means where I see x, I'm gonna be putting 0. So I'm gonna have f inverse of 0 equals to 0 minus 2 over 2, of which the answer is going to be -1. Which means as a coordinate, the y-intercept, remember y-intercept is when x is 0. So when x is 0, the y value is going to be 1. This is your y-intercept. That's how you must read this thing. This thing says on the graph of the inverse, when x is 0, y is -1. That's what it's saying there. And then now we need the x-intercept. We need the x-intercept. That's the one that can be a bit troublesome. So we have to let y be 0. And that will mean that on this, remember, equation, which is x minus 2 over 2, where I see y, I must put 0. But remember, this whole thing is our y, because it comes from this. It was y originally. We just replaced it with that. So where we see that thing, we put 0. So we'll say 0 equals to x minus 2 over 2. Then when you multiply by 2 both sides, you're going to find yourself having 0 is equals to x minus 2. Therefore, your x will be equal to 2 when you take the negative to the other side. Now that you have this means when x is 2, the y value is 0, because you said let y be 0. Using those two things, they are more than enough to sketch your inverse function. So what do you then do? The reason why I wanted us to use this one now is because I have a nice axis here. Right, I can, this is nice. So I can easily plot my graph. Do you see that?
Yeah.
Let's see. So now, remember, this is the x, and then this is the y. So on my axis, I'm just going to locate 0 and 1. So when x is 0, y is 1. So this is the point there. I go on 0, then I go 1 unit up. Along the x, I find 0. Then y says is 1. I move 1 unit up. So this is the point. So this is 0 and 1. Then this one, in terms of 2 and 0, I locate 2 on the x. Here is 2 on the x. Then I have to move 0 units up or down. So it means it just stays there. That is the other point. So I'm going to have 2 and 0. Then I can join those two. So when I join those two, it's quite easy again. I just draw my straight line there. Then, what do you know? I have my graph. Why is this graph seems like it's decreasing? Is the gradient negative? The gradient is positive.
Oh, so you made a mistake.
Where did I make a mistake, man? It does seem very wrong.
On the y-intercept, you said 0 and 1. Yeah, on the you said f is equal to negative 1, but then you put 1.
I put 1. Thank you so much, man. Thank you so much. Hey, you see, if I was alone, it was going to be tough to see that. So the thing is, that's when you must remember that when a gradient of this thing is negative, it looks like this. But here the gradient is positive because the gradient is actually half. So it can't be looking like that. So let's just fix that real quick. Let me take this. Oh, am I going to be able to remove this? Let me say that. Yeah, perfect. Even this, just remove them. So the point that I messed up, there is 0 and negative 1. So I think it's this one here. Let's just fix that real quick. Right. So we go to 0 and negative 1. That means it is this one. 0 and negative 1. Then I can now join the points. And then yes, now it looks very much normal. So that's what we have there. This is the graph for, remember, this is the graph for f inverse of 1. So you have sketched it. But now that I've spent all this time sketching the inverse, do I really need to find the y-intercept and x-intercept for the original if I want to also sketch the original here?
No.
What can we do?
We can just, the y value, make it the x value, and the x value make it the y value.
Great, we can just swap the x and y values. So here we have 0 and negative 1. I can just say negative 1 and 0, isn't it?
Yes.
Which is somewhere here. So it's going to be negative 1 and 0. And then I can say 2 and 0, I'll make it 0 and 2, which is here, which is going to be 0 and 2. So I just swap this and then I swap the other. Then I can join the points. So when I join those points, they give me something like this. This is what they give me. Right, very, very nice. Give me something like that. So this is the original, which is F. Great, man. Congratulations. Now you know how to sketch an original, you know how to sketch the inverse. And another way, you could have also sketched the original and just swap the X and Y to get the inverse, isn't it?
Yes.
But the only problem is that you wouldn't have the equation of the inverse.
That's true.
Yeah, so it means you would need again to work to find the equation of the inverse. Do you see that?
Yeah, so it's better to find the equation first, then sketch.
Exactly my point. So these graphs are always going to meet at this point, ne? They are always going to have a point of intersection. And this point of intersection, to get it, remember, you need to solve for X and Y, ne?
Yes.
So, because they like it a lot. So, but then, how can we find that point of intersection real quick? Now, I'm going to show you this, and then I think from there, it's going to solidify all of these things. Now, remember that the equation of the inverse, let me write, the inverse is as follows. It is, we said, I think it's x minus 2 over 2. Yeah. And then while the original, we said the original was, I forgot it. What is the original there? 2x plus 2. Okay. So it's going to be 2x plus 2. Let's write it there. 2x, f of x equals to 2x plus 2. Now, if I wanted the point of intersection, that means I must, solve simultaneously. But actually, since this thing can be written as y is equals to 2x plus 2, and this thing can also be written as y is equals to x minus 2 over 2, y is equals to that, at the same time y is equals to that. That means I can equate the two y's, right? So that means I can write that as what? I can say 2x plus 2 is equal to the x minus 2 over 2. Then to solve this very, very fast, you just have to multiply both sides by 2. Multiply by 2, and then this whole thing will be multiplied by 2. If you do that, you're going to have yourself 4x plus 4. And then here you're going to have x minus 2. Take x to the other side, you're going to have 3x. Take 4 to that side, you can have negative 6. You divide by 3, divide by 3, your x will be negative 2. That means the x value of a here is negative 2. Wait a minute, I could have easily gotten that using my graph itself. So it seems like I'm going to have negative 2 and negative 2. But let's actually find the other one. So the x, I can substitute it onto one of my equations, either here or there. So I'm going to have y is equals to 2 into negative 2 plus 2, which means negative 4 plus 2, which gives me negative 2. Yeah, seems like I predicted correctly. So that's what we have then.
Yeah.
Are we still together?
Yes, we are.
Hope I didn't lose you anywhere, man.
No, I'm still here. Still
Good.
following.
Good. So now we managed to find the point of intersection. Another way you could have found the point of intersection quite easily is to realize that on that point of intersection, actually, there is a line that is there. There is a dotted line that is there. Just that it seems like I'm not going to be able to have a dotted line. So I'll have to do it manually. So there is a dotted line that will be here. A straight dotted line. Next time I'm going to draw it with a ruler there. So here's a dotted line. And it will always be y is equals to x. The equation of that dotted line will always be y is equals to x. This is because an inverse of a function is actually the mirror image about the line y is equals to x. I'm going to repeat that. An inverse of a function is a mirror image of the same function about the line y is equals to x. So it's almost as if like this original is looking at itself, its reflection in the mirror. You see, that's why we say it's like a mirror image about this line. Are we clear?
Yes.
Good. So another way you could have actually found this point is to realize that since we already have y is equal to x as an equation, which is also passing through the point, I could have chosen any one that I like here. I'm gonna choose y is equals to 2x plus 2. Y is equals to 2x plus 2 because it looks much nicer without fractions. Then I could just say, oh, y is equals to x, y is equals to that. Then I equate the two y's. That means I'm gonna say x is equals to 2x plus 2. Then I could have easily now found the other one by saying negative 2 to the other side, and then I say 2x minus x, so which gives me my x is negative 2, which makes it much more easy. Now that I have negative 2, I can get y now by simply saying therefore y is, where I see x, I'm gonna put the negative 2, so y is negative 2. Then now I found it much quicker as compared to the other method. Then I have that equation as negative 2 and negative 2. So that is how we sketch an inverse. That is how we find the equation of an inverse. That is how we sketch the original. And then that is how we find the point of intersection. This is the inverse of a linear function. The other ones are going to be very much similar. If it happens that maybe you are remember that the original has a positive gradient, then the inverse is also going to have a positive gradient. But if it happens that the original has a negative gradient, what do you think it's going to look like? Let me just say I have something like this now. I'm going to start by drawing the, the line of symmetry, meaning that the line of y is equals to x, this one. So I start with it. This is the line of y is equals to x. If I were to draw the original like this, let's just say the original is like this, and actually we already have the equation there nicely. We're gonna have the correct coordinates. So this one here, it's 0 and 2, and then this one here is 2 and 0. Ne? If this is the original, I'm just gonna call it g of x. If this is the original, how can I get the inverse?
By flipping the values.
Let's flip the values then. 0 and 2 will become what?
0, 2 and 0.
2 and 0. And then 2 and 0 is somewhere here. So I'll write it. Yeah, 2 and 0. And then 2 and 0 will become what?
Sir?
2 and 0, this one at the bottom.
Oh, it will become 0 and 2.
Wait a minute. Seems like I'm going back to the same place, man.
Like, actually, what?
Right?
Yeah.
So if that is the case, how is this gonna look like now?
It's just gonna be on top of each other.
So it's just gonna be the same line.
Yeah. So if it has a negative gradient, then it's the same.
It's a negative gradient there. So are you saying we're gonna sketch it like this? This is the inverse.
That's what it's looking like. Unless there's another way to find it, then I'm a bit confused.
Good. Yeah, I asked this question because I know we like to flip these things just here on the graph so that we save time. But sometimes, you see, it can be a bit difficult to imagine it. You understand me? Because now it doesn't look like an inverse. You understand me? It's supposed to be a reflection, a mirror image. So to avoid this, right, rather what you can do is try to find it manually. See if it's gonna give you the same thing. So what you'll do is to find the equation of the original first. So the original is y is equals to mx plus c. So to get here, you need the gradient first, right? So the gradient is gonna be y2 minus y1 all over x2 minus x1. We're gonna get the equation of the original. So y2, I'm gonna write this as y2 as x2, x1, y1. So I'm gonna have 0 minus 2. Then I'm gonna have 2 minus 0. So that means I'm gonna have myself negative 1 as the gradient. So I have y is equals to negative x plus c. Now to get c, I substitute any of the points. I'm gonna choose 0 and 2. So y is 2 there, and then x is what? 0. From there I know that my c is equals to 2. So therefore this tells me that for the original, g of x is equals to negative x, because we have negative, and then plus 2. Negative x plus 2. And now that we have this as the original, now remember, you know the procedure of finding the inverse. The inverse, to find it, remember, you swap x and y. I'm gonna write swap because I'm hoping now you know. Swap x and y. So that means you're gonna have x is equals to negative y plus 2, and then make y the subject. So that means you're gonna have x minus 2 equals to, or I can simply take y to this side and take x to the other side. This is what I'm gonna have, isn't it?
Yes, it's exactly the same.
Yeah, it seems exactly the same, isn't it? Y is next negative x plus 2 and negative x plus 2. Ne?
Yes.
But why is that though? So the inverse is lying on the same line. Man, I don't want to lie to you. I do not feel too good about this.
Yeah, me too. Like what?
Yeah,
it's a bit confusing.
Yeah, it's very much weird, man, that the inverse can be on the same line as its original.
Why is that?
Well, come to think of it, it's actually very much correct, man. I know it looks weird, ne? But I want you to look at something. Let's go back here. Do you see that when it was going that side? Ne? I want you to focus on this part. Ne? Do you see it? Then I want you to look at this part. Do you see that they are exactly identical, and it's like they are looking at each other?
Yeah.
Okay. So it's like a mirror, in fact, this thing, isn't it? That dividing line. Now,
yes,
I want you to look at the one we just drew right now. I want you to focus on this part. Then I want you to focus on this part. Isn't this thing just like a mirror, and then this is looking at like itself on the mirror?
Oh.
Isn't it a reflection?
Yeah, it is.
Good. So it is still the inverse there, as long as they make a reflection about that line. So that is what I was trying to emphasize, that an inverse is a reflection about the line of y is equals to x. It's not just about swapping x and y, but it's actually a reflection about the line y is equals to x. Do you understand me?
Yes, I understand.
Good. if you understand that, say, perfect. Congrats, man. That is exactly what an inverse is. And all others that we're gonna discuss, like a parabola, exponential, they follow the same trend.